Okay, so let us start with Philly's second lecture and
Okay, thank you. So today I will start talk about perfect abstraction theory and virtual classes. So, but before that, I want to say that there are these two major mistakes. The first one is very serious. So on page 3, there's some comments on stabilization. And please just delete the entire paragraph. It's wrong, and I copied from somewhere and without thinking. And apparently that's a bad idea, so don't do that, okay? And also the 1.2, it's not correct, so you have to take a diagram. So think about it. So the Chlorine Morphisms, which we haven't talked about. But you have learned it for modular curves, so that should be something you know. And so I have to have the two evaluations on the same point. So that's something I forgot to put here in the notation. Oh, by the way, the first one, I have to thank Andrew Crash for pointing this out to me. Anyway, so the second one also to Melo and Filippo. Okay, so today, reference. Okay. So the main reference I'm using for this is from Graeber Pandariponte's inventionist paper on virtual localization, something like virtual localization. And I choose this above others because it uses very little of the language of stacks. Okay, so let me start. So X is an algebraic scheme, or it's a stack, the Riemann-Mumford stack. And so the data for perfect abstraction theory is there are two things. First is a two-term complex of vector bundles. Over X. So on X, you have a two-term complex of vector bundles. And then a morphism, I'll say this. Let me first copy it, and I'll explain this a little bit. See? A morphism of complexes from this two-term complex to something called cotangent complex. And this data has to satisfy two properties. As I said, let me first write down all of them, and then I will explain this. The morphism phi induces isomorphism in degree 0, and then induces it's a surjection in degree -1. And so to make our life easier, I will make assumptions that first, there is an embedding. So this is a closed embedding into one is smooth. So scheme or stack. So for today, you can think of everything as scheme mostly. And then the second assumption I'm going to make here is, well, do I need to make a second assumption? I remember I do. Okay, so the second assumption I'm going to make here is phi is a morphism of complexes. So I wrote all these, but really what I want to say here is, well, first of all, I need two terms, and you will see these two terms. I mean, as you probably saw from David's lecture yesterday, that you need you do need deformation abstraction to be two terms and two terms only, right? So that's these two terms. We'll learn that a little bit later. What these two terms should stand for in Grove-Witten theory, and then a morphism in the derived category. And I'm going to, so what does it mean to be in derived category? I mean, if you know, so and this, so it's a complex, so it's a category of complex of coherent sheaves bounded from above. That means it has to be like E, for example, E. So if you have any complex F, then you have a greater or equal to a certain number bounded from above. Less or equal to, sorry. So it could go to negative infinity, but cannot go to positive infinity. Make sense? And so, and that's what the cotangent complex live in. And in fact, by using the first assumption, so, and in fact, we only need this two-term complex. So we will, this two-term truncation of cotangent complex can be written as this I over I squared to omega y restricted to x. So I'm going to take this cotangent complex. I'm going to replace the cotangent complex by its two-term truncation, and this is sort of a what's a second fundamental sequence or something in Harshong's book, and omega y stand for the Kähler differential on y. So that just the if you're differential geometry, it will be the sheaf of differential first differential forms on y, like dz1, dz2, etc. And this will be your conormal sheaf of x in y. So I is the ideal sheaf of x inside y. Are we okay so far? And so since now and so what is I mean just the passing comment, because I'm already assuming that phi is a morphism of complexes. For in the direct category, if you have a morphism, which just means that you have to have a roof diagram which look like this. A morphism in derived category will be like E dot to L dot. If this is in derived category, which means if you can represent it by complex and complex, then you just have a roof going through this. It might not, this phi might not go directly from E dot to L dot, but you will go via roof, and this where this part, maybe I call S. S will be a quasi isomorphism, which means a quasi isomorphism just means this is a morphism of complexes which induces isomorphism on the cohomologies. So you first you replace that complex with another complex with exactly the same cohomology groups. Of course, you know how to do this in homological algebra, and then then that replacement has an honest morphism to L dot. So because I don't want to every time to write this roof again, so I'm making an assumption that the morphism phi is a morphism of complexes by itself. Does that make sense? So we don't lose anything by making the second assumption. We do this lose a little bit by making this first assumption, although in all the application of Gromington theory, well, maybe not all, but most of the application of Gromington theory, assumption A certainly holds. You can find smooth close embedding to smooth stacks for any M bar Gn x beta we defined yesterday. All right, so far so good. Okay, so that's the setup. And so this is called perfect-ish. Well, just sort of it's called perfect because it should have been called, the full name should have been the two-term perfect abstraction theory, but we'll just address this by this name. Okay, so as I said, Graeber, Pandari-Ponte, they started this by saying, look, let's first, how do I construct a virtual class if I'm given a two-term perfect abstraction theory? So what you need to do is to look at this diagram and carefully. And so, for example, when David was talking about this deformation abstraction, you can see that from this. You can try to ponder upon what's deformation abstraction from this diagram. And that's what we're going to talk about. But I'll first give you a formal definition of virtual fundamental class or construction. So first of all, you construct a mapping cone. Associated to the morphism of complexes. So we all familiar with mapping cone, right? Or are we okay with mapping cone? So, all right. So anyway, so the mapping cone of that, because it's just two terms. So this is a two term and the two terms. So mapping cone will be in three term sequence. Going like this. And so, so maybe okay, we call mapping cone. Is that mapping cone? So I'll call it cone of phi at so it will be E shift by +1 L, and the differentiation in C will be matrix of E goes so it's D E1 0 1 D. So that's mapping cone. So anytime you have a morphism of complexes, you can form a mapping cone. This is shifted by 1, and then the differential can be written like this. So this morphism of chain complexes. I think that's not calculates 1. So was that? This is correct. So you can check that against. Well, it depends on how you shift that. Right? So my definition of shift, E shift by n of degree m will be E m plus m. So that, I think that's. So -2 will give you -1, for example, because shift by 1 gives you -1. So that's how it works. Okay, so here's an exercise. Prove that the two conditions I associate with a perfect Chlorine theory, which is the morphism of chain complexes phi induces isomorphism degree 0 and induces surjection degree -1, exactly means that 1 plus 2 exactly means the star is this complex is exact. It's a sort of, yes?
When you say induces isomorphism in degree 0, projection in degree -1, does that mean on cohomology groups?
Yes, yes. In cohomology, yeah, that's right. Yeah, I should have said that. Yeah, thanks. Certainly, in cohomology algebra, you can always, you can always add that, this stupid pieces to that without changing cohomology. What I mean is, it induces isomorphism in cohomology in degree 0 and induces surjection in degree -1 in cohomology. So I'm grading these two-term complexes as in degree -1 and 0. Okay. Other questions? So this is a rephrase of the condition for a perfect abstraction theory. And so now what we're going to do here is, well, you see in the left, I did not impose injectivity. In fact, it will not be injective and in general. So what I will do here, I will take the kernel and call it Q. All right. So Q is defined just to be a kernel of that. My condition says it's exact on the right, but the left here is not exact. So so definitely this define this as set. So from this Q, so from this modified, now it's short exact sequence, I can form associate exact sequence of cones from 0 to Q 2e naught plus I over 2 omega y to x. I will form associated exact sequences of cones which will be due to this, which will be ty x. Then we'll call this E0. That is cone. So in fact, this is what called abelian cones. So does everybody know what cone means? I mean, look, really what you have here is once you have, say you have a coherent sheaf over X, then you can take sim, like this is in Harshon, right? So take sim of that. This is a sheaf of algebra over X, and you take what I mean by cone of this. It's just take what Harshon denote by ball-face spec of the sim. Okay, so that's what we say. And this is abelian because it's always generate. So this whole thing is generated at degree 0. So this, remember this sim, this will be like O x f, right? Things like this. Yeah, sure.
So that thing actually looks like a cone, but I don't see why the mapping cone looks like a cone.
Oh, mapping cone is, look, mapping cone is something which you have to, if you want to see what cone is, you have to go back to topology, what the topologists say about mapping cone. So this is geometric cone, but the mapping cone is really, if you have a, so this comes from topology when you have so you have a continuous map from X to Y, and you can cone it in this way. But
that also looks like a cone, doesn't it?
yeah, it also looks like a cone, but then we extract homological algebraic information about that topological construction. That would be a mapping cone. But we can talk about this later. Okay, so but if it doesn't look like you don't find a cone, yeah. Anyway, so you will. We can talk about this. Yeah. But anyway, so this is what I mean by abelian cone. Means it just means it's generated by this. And in general, for example, this is a abelian cone, and then you have a cone which so this, for example, when it's not called abelian cone, then it means, for example, you have this normal cone of y inside x. This is not this sim construction, but you have to take spec of this O direct sum R. Sorry. Maybe I'll just write this. O I n plus 1. So this is usually what called normal cone. And this will be in, I think, Kai Behrens and Barbara's Fantekis terminology will be called abelian hull of that cone. So this is a usually called normal cone in Fulton's book. And this is, well, not just in Fulton's book, but I mean, you can find it in Fulton's book. And this is sort of certainly that if this is all generated in the degree 1. So this is generated degree 1, and so certainly this map to that. So this and therefore the corresponding cone so this well that's okay, so that's sort of an explanation of what I mean by cone, in particular abelian cone. Abelian cone, as I said, is a sim construction, and usually cone you can have it's a graded algebra, and in all the cases of this graded algebra, I'm requiring that it's generated in degree 1. Okay, so that means you can always find this surjective map because it's generative in degree 1. So this guy has more relations. Well, this guy relation all generated by degree 1 anyway. So, questions? Yes.
What does it, I mean, okay, first, E lower 0, so should that be E upper 0?
Yeah, so I'm going to explain this. Okay, so this guy is just defined to be a cone of E0, E upper 0. Okay, but this guy, because it's a vector space, so it's basically so if you think about this as sort of well, I mean, there are two ways to think about vector bundles. One is think about locally free sheaves, and that's how I think about it here. And so this is just the cone of the locally free sheaf is what Fulton would call vector bundle. One is locally free sheaf, one is vector bundle. Does that make sense? So this is again, this is generated freely, locally, and this is just using that free generator to construct a vector space fiber-wise. Yes.
The section of E0 should be the dual of E0.
Yes. This, as I said, this is a function. You can think about this as a function, and this is the space. So it's dual in this way. Right? Think about Cn. The dual is just the coordinate z0 up to, z1 up to zn. So I mean, two spaces are dual to each other. And what I haven't explained is exact sequence of cone. What do I mean by exact sequence of cones? This is a little bit complicated. So exact sequence of cones means that if you have two, so I mean this is something which usually. So what my understanding here is that exact sequence of cones has to come from in the short exact sequence. It will be cone, and this guy has to be a vector bundle. So let me give you one definition of exact sequence of cones. So exact sequence of cones, this one is the following. So if I consider two cones, C is this, maybe I don't have enough space. I should use upper one. So exact sequence of cones has to come from two cones and one vector bundle. So definition, we first start with two cones, which is this guy's spec S, where S again is a sheaf of OX algebra, and you have another cone S prime, the same thing, and then we require that again all these S0 and S prime 0 has to be OX, and it's generated in degree 1. Although this requirement might not be needed here, but I impose it everywhere across the board in today's lecture anyway. So an exact sequence of, a morphism. So I first define a morphism of cones. So if I want to give you a morphism of cones, this has to be given a morphism cones given by has come from the algebra, your sheaf of OX algebras. Of sheaf of graded OX algebra. Yeah, I should say graded. The gradient gives you the cone structure. This is important, so maybe I graded OX algebra. The gradient gives you the cone structure because it gives you a sort of C star action on that, on your space. Okay, so it's a morphism of so a morphism of cone has come from, so as I said, we know what's a morphism of sheaf of graded OX algebras. And because cones are constructed out of that, so I define the morphism of cones this way. So that's the first thing. And then, so again, if you, I want to say this, if you have locally free, then you can, then there is this. Again, this is a vector bundle that's going this way. And then, for example, we can think about E0 or omega y restricted to x as locally free sheaves. And then Ty restriction x will be considered as a vector bundle. Then, so given, if you are given the following things, C to C prime, you have phi, and then certainly this is also a cone, but it's just a sort of better kind of cone, right? So you can think about this as locally free sheaves, and then you can generate that. So by this notation, I mean you take sim of that, become graded OX algebra, and take spec of that. That would be your E, right? So this. Be more careful. I have to write like spec sim dot E, etc. So, but you understand what I'm saying. If I just write a sheaf without being an OX algebra, I mean take a sim, become OX algebra, etc. So this is also a cone. Well, certainly it is a cone. It's just an easier kind of cone. Firstly, a abelian cone, and then secondly, it's actually this generator is actually freely. There's no relations. And so you have these two morphisms. You're given this. So if you're given phi and psi this way, and we call the sequence exact. If, first of all, I think two conditions. First, I know this thing is surjective, so that means on the function level, the dual level has to be injected, right? So that means And since I defined this from phi tilde, I will say this phi tilde is injective. That explains the surjectivity. Okay, questions? So that's the first thing. And the second thing here is that because this is injective, that means on the level of functions, it has to be surjective. So again, so this phi tilde from S dot to sim, this is surjective. So that explains this part and that part. Now we have to explain the middle part. So that explains here and here. Now I have to explain what's exact in the middle. So I think here, I mean, those who are actually more knowledgeable should correct me. But I think here, the correct definition here is locally on X. Okay. So this should be subjective. Is injective. So this should be something like that. I know this is injective to that, so I can consider this a sub-sheaf of graded OX algebras. Okay. What I'm saying here is that locally, I want this to be exact. Locally to be trivial. There's no extension. The short exact sequence, just like we talk about short exact sequence of sheaves, locally, it will be just direct sum or product in whatever sense you're talking about. And that is the definition. Depending on which topology you're using. If you're on X, you're using Zariski topology, that'll be Zariski locally, and if you're in étale topology, that will be étale locally, etc. Yeah.
Can a sheaf be recovered from its cone?
Can sheaf be recovered by its cone? Yeah. Let's see. Can sheaf be recovered by its cone? I think so. Any objections?
I mean, clearly, if the sheaf was locally free, then you can just take the sheaf in sections of the cone
Yes.
and then dualize.
Yeah.
But if the sheaf is not reflexive.
Yes.
Yes, just take global sections.
Yeah. You.
Yeah.
No, but that would give you, at least in the locally free sheaf, wouldn't that give you the dual of what you want?
No. Well, they are dual to each other anyway. Anyway, I believe that's probably in Harshung's exercise. Like, he has this exercise of ball phase spec, and if you check that, it's all there. Okay, so to say this more carefully, I can say the following. So locally on X, there exists a locally free subsheaf E tilde such that which maps isomorphically to E such that S prime dot tensor with, to be honest, I have to say this, tilde, which go into, it's an isomorphism. So that's basically, I just say, what I said here more, in a more down-to-earth term. Okay. Actually, I'm not really the best guy to explain this. I know many people in the audience who are actually more knowledgeable about this subject than myself is. But anyway, so I was assigned the task, so can't complain, right? So. Okay, so that's my definition of an exact sequence of cones. Questions? So once we have exact sequence of cones, then I know what I mean by this sequence is exact. So basically, as I said, exact sequence of cones, it's very similar to the dual sheaf has to be exact, except I also need to say that one thing you have to be careful is that E has to be a vector bundle, and locally it has to be trivial. The extension has to be trivial locally. This is a little bit, I think Fulton's definition has a typo there. I corrected that. Maybe my correction, it could be that Fulton was right, I was wrong. So you should check that. Okay, so this is our exact sequence of cones. From this exact sequence of cones, I'm going to define another cone, which then we will use that cone to construct the virtual class. Okay, so what is that? Okay, so we do have this. So remarks. Since we have E minus 1 subject Q, so definitely cone will be injective to E1. Right? By definition, I choose Q to be to factor through that, so that's definitely that. Okay, so and also, this one I said already. So maybe I should reverse this. Subject also means that the cone so this is defined by that, and this is defined by that. So it's like this. Okay, then, okay, so that's two remarks. And then I'm going to define D to be the normal cone of X in Y fiber over E0. And here is a fact / exercise is that I'll explain the terminology in the next board, but I want to write this down in the same board so you can see this. D is called TY cone, or actually it should be TY restricted to X cone. TY cone. I'll explain what TY cone means. And secondly, if you quotient that by TY, this is what. So I have introduced another name. This is a vector bundle cone. What do I mean by that? I'll explain this. Okay, but just say there is something called vector bundle cone. And yeah, so and then you can do a quotient of this cone by this vector bundle, and they will embed into this cone of Q. That's a statement. And now I will explain what I mean by a vector bundle cone. So are we good now? So I'm going to lower the board. So what is a vector bundle cone? Well, basically, what is a vector bundle anyway? Vector bundle is a vector. It's a family of vector spaces, right? And vector spaces certainly is an abelian group. So I can consider. So if I have this, if you think about fiber-wise, and I can think about the cone being acted by a vector space as an abelian group. So and that's what we call vector bundle cone. So let me give you a more explanation. So again, the key point is just basically because a vector space, you can consider a vector space as a sort of abelian group, or in this case, abelian group scheme. So let me say this. So if you have definition, if E over X, which is a vector bundle, and you have this C over X, which is a cone, and such that the C is actually a abelian cone. No, C is just a cone. So I will have to write this as S dot. And again, we always assume, as always, S0 is OX. This is S dot is generated in degree 1, or locally generated degree 1. So, and then if you have a morphism of cones, so given a morphism of cones, E2C is a morphism of cones, which I just defined. Well, it just means a dual sheaf of OX algebras induce homomorphism in the dual sheaf of OX algebras. So, and obviously you can pass this as I just said, called abelian Hall. So abelian Hall, because this is already defined by sim construction. This is not, but sim construction, as I put on the downboard, that it has a map, so you can pass this to. So the abelian Hall of E is still E, but abelian Hall of that, which I'll write AB. Okay, so as I said, this is objective to that, right? Because the sheaf of algebra, sim. Let me write again. Sim one surjects S dot, because it's generated in degree 1. So you have the cone of S inject to this, what we call abelian of C. So that's this. And this d tilde, so because now this is also a abelian group, so this d tilde induces a homomorphism of abelian group scheme and so because it induces, now what do I mean? But this is a subscheme of this abelian group scheme. So now I can ask whether this this cone is invariant under this. So if C is invariant under this action, then I will say this then we'll call this C E cone. Does that make sense? So this cone embedded into an abelian group scheme, and you have a homomorphism abelian group scheme, right? So so that means this C, this E also, because it acts. So I mean, by this it acts on. So if a homomorphism groups, that means that you can say that in other words that the first group acts as second group, right? By this homomorphism, right? It's like first course in algebra. Like first chapter in algebra. And then, but this sub-scheme might not be invariant under this action. I know this, the whole group certainly is, but the sub-scheme might not be. And if sub-scheme is invariant, then I call it E cone. And so the statement I made, which you need to check, is that the D I just defined is a Ty cone. So it acts on D. The D is an invariant subset of abelian Hall, and then the quotient actually embed into the cone constructed out of Q. So that's what the statement I made. So I should have switched these two boards, but it's too late now. So anyway, so what I mean by this is this D is Ty cone, and therefore Ty acts on D, and the quotient is the subscheme of this cone. All these, take some time to digest. Unfortunately, there is no very good way of doing this. I will give you a few examples, but that's to digest these. It probably take you some time. Yes.
I don't understand what's invariant means.
Sorry.
Definition. Invariant.
Oh, invariant means, well, if you have a space, if group action in space, right? So it moves one point to another point. Some of the point, so I can take a subspace of this space. Invariant, it means very simple thing. It's like you. So what's a group action in space? It just means you take it will go to another point. Every point go to another point, right? So if I take, say, this, then the point here will go outside of this point. It won't be invariant. But if I take, say, an orbit of the action, then it will be invariant because every point will stay, after action, will still stay in the same subset. Well, invariant, as I just said, it's G. So the group. So okay, if a group acts on say V, okay, and then you can take a sub-scheme of this V, say Z, and what invariant here means, if you G acts on Z, it's still inside Z. After action, still lie inside Z. G acts on subset, it doesn't have to lie on the subset. It's invariant if it still stay in the same subset. Okay? Okay, so now we have this. You might be thinking, hey, there's so many exercises. I've probably put all the difficult stuff into an exercise, which is not completely true. I mean, the exercises are not difficult to work out. You have to unwrap all the definitions, then you will see the exercise. Well, some math is like this. Some math is, once you understand everything crisply clear, the statement become obvious, right? And some statement won't. I mean, even though you understand everything, it's still a marvel that why this equality will hold. And this is belong the first type. Once you understand every definition and statement correctly, then these exercise or the fact I quote becomes tautology, basically. And so that's why you need to think about these. Okay, so, all right, so what's the definition of virtual fundamental class? Now here is that so I take I define D to be the quotient and then this lies in C of Q, and as you know, I just said the C of Q again lies in E1. Right? So I've shown all these sequence. The first ones I said is an exercise, and second one is is a tautology I just explained by construction. So once you have this, and then you define the virtual class to be okay, so this D upper sheik is a refined intersection of that, which I will explain. So you have this X, and then you have E1, and of course this is a zero section, so 0 by 0 section. So every vector bundle over X, I do have a tautological zero section, right? So forget about the projection. I'm just taking a zero section. And now I have this D ver inside E1. I can take what Fulton called refined intersection of this. And this is what called Are we okay with refined intersection? Okay, good. So that's the definition of a virtual fundamental class. Not too long, right? So, yeah. See, we still have time. So now I will apply this to Gromwitten theory.
Finally, it doesn't use Q, right?
Sorry?
So in the end, it doesn't use Q.
It does not use Q? Well, yeah. I mean, this Q is sort of a transitional figure. I mean, I can just exercise this Q but it's easier to put this Q into exposition so that I don't have to, I will explain, so I was told that I definitely had to explain what this stacky approach is, so I'm going to explain that later, but I noticed I only have 30 minutes, so I will speed up a little bit. Anyway, so the reason was some of you wanted to know what this, and maybe when you read the literature, people use different terminology. So I'll explain the terminology. But anyway, so are we good so far? All right. So now I will explain what we will do in Gromwitten theory. So what does this has to do with Gromwitten theory? Well, in Gromwitten theory, of course, I want to define virtual class for n bar Gn x beta. So X will be n bar Gn x beta. So unfortunately, that's a mistake because I use X here and I use X there. These two X are not the same. Yeah, I remember when I was a child, I used to do a program, like basic programming, and this programming basic you can always let x equal to x plus 1. That's always something you can do always. And so in Gromov theory, so the x will be m bar gn. Now I'm going to avoid x here. I will go back to this to be x, but just for today, my smooth projective variety will be v. Okay? Because I already used x for that. I realize this is a mistake, but I've done that. So, okay. So how do I get the two-term complex of vector bundles? The first question is, how do I get this? Well, I know, okay, the first question, right? Because I want to construct virtual class for m bar g and v beta. I have to first tell you what E dot is, all right? And how do I construct this E dot? It's quite simple. You just take universal curve. I know I'm, my board writing might be a little bit schizophrenic because I tend to like to write x, but I already use x for something else. So let me call this pi. All right, so and this E dot, I will not define E dot, but I will define E dot dual. This will be the same as, in terms of complex, to be, and you have F to V, TV. So I pull back this, and this is a certain two-term because this is a family of curves. So only H0 and H1, no H2, right? That's certain two-term. But it's not a complex. It's certain two-term complex, but not vector bundles. Two-term is okay. Two-term complex, okay. But vector bundles, no, not yet. I have to make sure I construct a vector bundle here because these two terms are not two-term complex of vector bundles. It's two-term complex because of dimensional reason and Gordic theorem, but it's not vector bundle. So to construct a vector bundle, it's very straightforward. It's a sort of a standard treatment in this algebraic geometry. All right, so how to make sure this is isomorphic to E0 to E1. How do I do this? Well, I will first do the following. So let's see. I'll first find let L be an high ample line bundle. And then you can construct, so then what we want to do here is to construct a vector bundle sequence of this. So let me call G this pullback TV. And I want to construct a two-term complex of vector bundles out of that. So what I will do here is that for all n very, very large, I have the following thing. So if you do the pi lower star G tensor with L n pi upper star. This will surject G n. And this is just, well, it's basically say if I tensor it enough time, becomes generated by global sections. Right? So take ample, then take a very high power and tensor with any quasi-coherent sheaf becomes generated by global sections, or coherent sheaf actually. So the second thing here is I can also make hierarchical march vanish. We have for n greater equal to, also not greater, n is equal to 0, and then R0 of this that is something, because I take any pi ample line bundle, then I can do that. So now what I need to do is to take this. So so I will take define f to be this thing. So pi upper star pi lower star of G tensor by Ln for any n. Then I tensor, after this, I tensor it back. And then, so this certainly by first one, this surjects to G, because I tensor it back, right? So that is good. So this is exactly the first part. And now I call the kernel K, because it's a surjection of vector bundle, so this will also be vector bundle, right? The kernel of surjection of vector bundle is a vector bundle. Co-kernel might not. The injection of vector bundle might not give you a vector bundle, but certainly surjection give you a vector bundle. Okay? So now I can form a non-exact sequence of this, and which you will get here is, I'm going to write a shorthand, so R0 of K, R0 F, R0 G, then R1 K, R1 F, R1 G, all right, so this guy is trivial on the fiber. Only this happens, so this will be 0 by the third. So maybe I'll put this 1, 2, 3 or something so I can refer them. By the third, I have this equal to 0. So this is by 1. Right, and because of this 0, this has to be equal to 0 as well. And this is exactly what I want, right? Pull back and push forward. G is this. So that is exactly what I want. This part is exactly what I want. And so, but these two, because these two vanishes, so that means these two have to be vector bundles. So I'm done. Okay? So I find two-term complexes vector bundles. Yes?
Just quick thing. When you
Yeah.
write definition dot at, do you mean that to be an F upper star?
F.
On the left side of the board, it should be R pi lower star upper star. No big deal.
Pi lower star. No, here. No, here I want to push forward here. So this is my X. So I construct this out here. So this is, you see, it's pi lower star of G, exactly what I want.
Yes, F upper star.
F. Oh, yeah, sure, yeah. Thank you, yeah, certainly. Otherwise, it won't make sense, right? you know, when you read paper, if it's a typo, you know, it's there, obviously a typo, it doesn't make sense that way, then it's easier to guess which way it goes. The horrendous one is like when it could mean 10 different things and you don't know which one to choose. Yeah. But anyway, no excuse for any mistakes. So that's two-term complex we found. Okay. So how do I construct this virtual class, which I'm going to be a little bit sketchy. So usually what we do here is not to construct sort of this what you would call absolute virtual perfect abstraction theory, but to do it fiber over fixed curve. So we'll construct a perfect abstraction theory fiber-wise with fixed curve. Okay. So that's how we usually construct virtual class out of Chlorine theory. So I'll explain this a little bit. In Chlorine theory, we'll construct with fixed curve. Fixed curve means complex structure and everything of the domain curve is fixed. Oh yeah, so I forgot to say, how do I find this pi ample line bundle? Well, this is easy. So L, I should have said this EG. You can choose L to be relative dual line sheaf of your CX twisted by your curve and tensor with F pullback of ample line bundle. What do I? Maybe give it a little bit power. So like third power is certainly is enough. Maybe ample is good enough. Yeah, I think ample is good. But anyway, so something like this. Well, if the map is trivial, this part will be ample. Okay? And if the map is not trivial, this part will give you ample. This fiber-wise. So this guy will be a pi ample line bundle. Does that make sense? So that's the way, one way to find pi ample. I mean, certainly the map is surjective, so you can always find the relative pi ample line bundle. So okay, so that's usually what we do here is to find. And how do I do that? Well, I want to fix curve, but I don't want to. So the one guess would be to take this x n bar gn v beta, map that to n bar gn. But this is bad because I change the curve. When I do this, I might have to contract unstable components, right? That's the only bad thing. So instead of doing this, well, I mean, here is you have to use some kind of stackiness, but very mildly, that I change this to a sort of Artin stack of pre-stable curves. So what does that mean? That means I don't do any stabilization. I just take the domain curve and map to what the class of domain curve is. And if I do this fiber-wise, I mean I definitely fix the curve because I do nothing with my domain curve, right? So I fix my domain curve. That's what I mean. I do this fiber-wise. So now you can also have this class over here and map to x. Oh, sorry, v. And so I'm doing this fiber-wise. So I fix, say, tau here. And here everything will be over tau. But this is okay. Why? But this gives also the desired virtual fundamental class. Why? Well, you think about this, then it will be very clear. Because, well, okay, so maybe you have to think a little bit harder than I suggested. That this guy is actually smooth. Well, in the first week, you learn the deformation theory of pre-stable curve is unobstructed, right? Any nodal curve, it doesn't have, you don't need stability condition. Deformation of nodal curve is unobstructed. You can, if you have a node, you can always deform the node, right? And you actually know what the deformation is locally. Does that make sense? And for a moduli problem, deformation space gives you the smoothness of this. Deformation theory being unobstructed means the moduli stack itself is smooth. The same way you prove n bar Gn for stable curves is a smooth stack. Okay? Does that make sense? All right, so I have to use, so since it's smooth, so you don't need obstruction. So you can go from this sort of relative perfect obstruction theory to absolute perfect obstruction theory by a simple manipulation. So you have this E tau here map into L tau dot. So L tau dot, I mean I fix my domain curve, and then so here fiber wise I have, well, this guy I have L, and fiber wise I also have L tau. Okay, does that make sense? It's just two-term truncation of embedding to a global smooth stack. So this is what we constructed by using this. Now you can globalize this, saying, look, certainly I have this Lx, where x is this. This is I build on x tau, and this is just entire x. And certainly this by sort of this kind of mgn, and then tau. And this is some kind of distinguished triangle, which I will not explain. Well, I will not explain this too much of distinguished triangle. But anyway, so this guy, you can have, then you can extend this to this. So in Gromwithian theory, as I said, usually what you constructed, oops, oh, here is a chord. Usually what you constructed is here. But it doesn't really matter. But if you want to construct your obstruction, this guy has no obstruction. So E is the same as L. And so this is what you want. This is what you constructed, fiber-wise, sort of family-wise. And this is what you want. And you can easily shift to what you want by just this simple extension. And because everything was done in sort of a derived category, there's a sort of distinguished triangle of derived category, etc., etc. So, which I will not get into. I will make this assumption that I'm not going to use derived category. And here I just tell you, you can extend this because this MGN is smooth, no obstruction. Okay, okay so far. So that's obstruction theory we have. There are two other things I might not be able to finish. One thing is I was told I have to explain what the intrinsic normal cone is. And even though I don't understand them, I will try to explain it anyway. Because so just to, well, the good thing is like once you know this, you can shift between the terminologies This is just basically this Graeber-Pandari-Panda exposition is sort of a more down-to-earth exposition of what you will find in Baron, Van Tecke, and so okay. So this here is a comment on Baron, Kai and Barbara's original exposition. And that was sort of a so this is equivalent to above, of course. So here is from this E dot, right? And you form a dual. Again, the E lower dot, which will be E0 to E1. And again, so I can form the stack quotient of group schemes. All right? So you can form this called E1 quotient by E0. This is really a stack quotient. Like here is a quotient, right? It's a fiber-wise abelian group quotient by an abelian group. Okay, so the second part here is from this. I know this. Excuse me. That you have this action of Ty on a normal cone, and then so this again same C as that C is Cxy quotient by x. That is what they call intrinsic normal cone. And I have to choose. Look, I choose right? Y is something I have arbitrarily chosen. The eventual result I constructed should be completely independent of Y. Riemannian manifold. But instead, I do an embedding. And then that everything I can same here. So what so that contains no of choice. Independent choice of embedding. If I don't have a global embedding, I take X, find a chart. For each chart, I can group these quotient together. It's completely independent of choice of this, and because I global embedding of X to Y, but locally I can. So that's why it's called intrinsic normal cone. The third part here is that very similar to what we this two close embedding. Pointed out that I did no Q here in this. And the Q is there.